Computer Systems, A Programmer's Perspective Textbook Review. Today we will be starting with Chapter 1 review. Let's get started. So Section 1.1, Information is bits plus context. In this section, a computer system is defined. What is a computer system? Computer system is a collection of hardware and software that runs application programs. Now, there's three terms in there: hardware, software, and application programs. And how does this work together? So what is hardware? Hardware is the physical devices on a computer that actually transfer the electrical currents and manipulate them. Software controls the hardware of the computer, and more specifically, an operating system, which is a type of software, is the main software component in a computer system that controls the hardware and tells it what to do. And then lastly, you have application programs, and this also is software. However, this software uses both the operating system and the underlying hardware to run applications that we all use. So there are two types of files in a computer system: text files and binary files. Binary files are ones and zeros, of course, because that's all a computer can understand. And text files are files that represent characters. In other words, the letter A, the letter B, right? And how does a computer do this? Well, it uses an encoding scheme. So a computer does not recognize the letter A, it only recognizes binary. So it has to convert the text into binary. It does this using an encoding scheme. An example, one of the more predominant encoding schemes and one of the earlier ones, is ASCII. That's ASCII. And the ASCII encoding scheme is a one-to-one correspondence between character and binary number. I think it's 1 byte in length, but I forget. Anyways, so for example, this isn't the case, but the Latin character A would correspond to the binary 1, and B would correspond to 1, 0, right? And C would correspond to 1, 1. So it's a one-to-one correspondence. Another encoding scheme would be UTF-8 or UTF-16, 8 being 8 bits, 16 being 16 bits, and that is a more complex encoding scheme because it isn't a one-to-one correspondence. So I'm not going to get into how UTF works here, but basically know that it isn't a one-to-one correspondence, and it uses a different mapping scheme to translate a text character to a binary number. Also, UTF-8 and UTF-16 has many more characters that it can encode to binary versus ASCII. So UTF-8 and UTF-16 are more common today, especially in areas like web development, where things are needing to be written in multiple languages. So multiple different types of characters are needing to be expressed as binary. Lastly, it goes over information as bits plus context. And what this means here is information to a computer is in the form of bits, a 1 or a 0, right? Or a stream of bits, multiple ones and zeros. However, what 1 and 0, so for example, 1, 0, 0, 1, 1, that binary number right there, that could mean one thing to one program and one thing to another, right? It depends on what we assign values to. Maybe we say all binary numbers that start with 1 add or after 1, it says, hey, store whatever is after this binary number into memory, right? Or maybe it'll be 0, right? So it's completely dependent on how you're viewing this binary number, right? So that's what it means by information as bits and the context in which you view them, the bits in. Section 2, programs are translated by other programs into different forms. Now, The language used in this book is the C programming language. So of course we're going to be going over how C is compiled and not other programming languages. So the basics is C, a programming language, that's a text file, right? It's written in characters in these programming constructs with while loops, for loops, etc. Needs to be understood by the computer. So a compiler's job is to turn this text file into machine language, or a binary file filled with ones and zeros, and then ultimately make it an executable object program. What this means is that when you, for example, type the name of the file in a shell, or click on the file and type run, the computer will run it, because that's what executable means. Like, it can run, right? Because you can just have a normal file with ones and zeros that doesn't, you can't just click run on it. It has to be a specific type of binary file. Now, the compiler driver is basically a it's the part that controls the compiler. So within a compiler, you have multiple different options. I'm not sure if anyone who's watching this has ever used the GCC compiler for C, but you have a lot of different options when you use a compiler. You can say, hey, I just want the machine language. I just want to convert it to machine language, or I just want to convert it to assembly language, or I want to use this file and compile it also with these two other files, right? So that's sort of what the compiler driver manages. So the basic compilation process of a C text file would be, first, it goes through the preprocessor and turns it into, so let's take the hello.c file. So goes through the preprocessor, gets turned into hello.i, goes through the compiler, turns into hello.s, assembler, hello.o, and finally the linker, which turns into whatever you want the executable's name to be. We'll just say hello. So what the preprocessor does is, if you are familiar with the C programming language, there is a certain character, namely the hashtag character, that you can put in front of words, for example, in front of imports. So hashtag include this header file, right? Example.h, example being the header file. And what the preprocessor does is basically copies and pastes this header file where you had the hashtag include. So the preprocessor basically looks for the preprocessor directive, which is the hashtag, and does a few simple things like copy and pasting. It doesn't analyze the code or anything like that. If you are familiar with compiler design, it's okay if you don't understand this point. All it does is lexical analysis. Now, moving on to which basically means it parses syntax. Now, moving on to the compiler. The compiler actually evaluates the meaning of all the code, and so not to get too much into compiler design, but this is where you get your abstract syntax trees and semantic analysis and compile time exceptions and stuff like that. Then it gets to the assembler, and then the assembler turns it into object code, or let me mention this. The compiler will turn it into assembly language. And what assembly language is, it's basically machine language being ones and zeros. However, it's in a human readable form. What does this mean? This means, let's say, the binary number 1 when fed to the processor means store data, and then you have like the value after it, right? So in assembly language, instead of writing 1 whatever, you would just say store, the word store, whatever. So it's a human readable form of machine language, basically. And the assembler will convert this into the actual ones and zeros, the machine language. And finally, the linker will handle everything else. Now, what is everything else? Well, sometimes the program that you're writing depends on external libraries and other programs within the computer. For example, the Hello World program uses the function printf from the standard C library. Well, this is where it would resolve that dependency and make sure this object code has the ability to call that function. So that's why it's called the linker, because it's linking different object code files. And then finally, it turns into an executable. Section 1.3, it pays to understand how a compilation system works. So a compiler naturally does optimizations that are fairly straightforward. For example, even though you're writing the programming language to do one thing, when the compiler turns it into, let's say, assembly language code, it may recognize, oh, there's a quicker way to do this. I'm just going to do it for you because it doesn't change anything except it's faster. So that's compiler optimization. However, of course, it isn't enough because a compiler isn't all-knowing, and you're better off writing the quicker code first. Now, IA32 and x86-64 are instruction set architectures, basically, and so those are two common ones. And although we'll get into this more in the book and later in a different section, but an instruction set architecture basically describes what instructions a computer can do. Finally, you have buffer overflow vulnerabilities. So if you're familiar with a buffer is basically a way of storing data, and buffers have fixed sizes. So if you store more than a buffer can handle, you're essentially overriding some data somewhere, because and this is a common mistake of not checking, or this is a common way to hack a program, is to overflow the buffer, and then in the overflow data you would describe, some malicious thing to do. And knowing how this code works on a deeper level is going to help you prevent this, and that is discovered in a later chapter. Section 1.4, processors read and interpret instructions stored in memory. Okay, after reading interpret, I forgot to say, so with declarative languages such as the C programming languages, I just forgot to mention something earlier. Let me just go back up to it. Okay, so compiling. It's not always done like this. For example, in the Java programming language, instead of compiling to machine code, you compile it to bytecode. And the Java virtual machine, we'll get into what a virtual machine later is, but think of it as a virtual computer. That's its machine language, the bytecode, and it understands how to do that. And you can only run it on your computer if you have the Java virtual machine installed. Another way of doing this is with an interpreter, and a compiler will take a whole file at once, figure out what it means, and produce the machine language. However, an interpreter reads a line at a time and then executes it. So the end product of the compiler or the compilation doesn't do anything. It's just an executable. You still have to run it. However, an interpreter will do these things at the same time, line by line. And there's advantages to each and disadvantages to each. Okay, so 1.4. So a shell is basically, an example of a shell is a terminal or a file manager application on your operating system. And what a shell is, it's an interface to the operating system. You can move files around, you can edit files, stuff like that. You can run programs, and the terminal or the command line interface, that's what CLI stands for, is the most common shell. It goes over buses. So how do the ones and zeros travel from different parts of the computer? They travel by buses, right? Because bus is a transportation vehicle, so that's why it's called bus. And not to get into too much of the architecture of buses, but you can, and remember, the hardware is very complex in a computer, And oftentimes you don't need to understand its full complexities and how it works in order, or how it's exactly implemented, like everything about it, in order to understand how it works. You can sort of get the general idea without all this. So, for example, in this book, they give an outdated description of what a bus is. For example, they talk about the system bus. And the system bus is basically the main bus in the computer, right? How all the data gets transferred around. Well, that's not really how it's done anymore. Now there's multiple buses, some with higher priority than others. Um, I'll explain maybe a little bit more about this at the end of this section. So you also have I/O devices, and I/O devices are your keyboard, your USB, the network even, the display, and the storage, the disk space. So I/O devices have their own I/O bus, right? How they communicate with the rest of the computer. They also have controllers and adapters. So the information input into a keyboard gets converted into something that the computer can handle. That's what a controller and an adapter does. The difference is controllers are built in with the computer, and let's say you change your graphics card, then you would get an adapter for it. They're basically synonymous. It's just controller comes with the program, computer, adapter is something you install later. You have your main memory or your direct random access memory. And main memory is volatile. That means when you turn your computer off, it gets deleted. So where do you need to store the data? You need to store the data on your disk. And however, you can't work with data on your disk. So whenever you need to work with data, you need to bring it from disk to main memory. So yeah, that's how that works. And you also have the CPU, the central processing unit, and that is sort of the brain of the computer. It's where all the instructions are executed. And it's probably the most complex part of a computer. So you have a register file in the CPU that contains a bunch of registers. Registers are small things that store data, basically, right? They can maybe only store like 32 bits or 64 bits or even 16 bits. Depends on the computer, the processor. So a register file is a bunch of registers, and of course the CPU has a bunch of registers, and that's the data the CPU works with. So really, if you wanted to add two numbers, you would have to, from a file, you would have to get the file from your disk, put it into main memory, or at least part of it, that have the two numbers, and then put the two numbers from the file into a register so the CPU can work with the data, because the CPU can only work with the data in the registers. Now, a specific register is the program counter, and that basically stores what instruction to do next. So ISA, instruction set architecture, that's basically what instructions the CPU can handle. And the ALU, the arithmetic logic unit, is the brain of the brain, let's say. It's the part in the CPU that actually does the executing, the adding, the multiplying, the Boolean logic commands like XOR or AND. And then finally you have a microarchitecture. So the instruction set architecture is basically an abstraction. It's not like exactly how it is, but it still describes how the CPU works and the instructions it can handle, whereas the microarchitecture is like the exact way it's implemented, because it's much more complex. And in order to understand the CPU, you really don't need to understand the microarchitecture, just the ISA. So some basic commands the CPU, or more exactly the ALU, can do is load, store, operate, jump. So jump to the next number in the program counter, so jump to the next instruction, operate on some data, load some data from the memory to the CPU, or store some data from the CPU to the memory. You have DMA, that stands for direct memory access, and basically what that does is instead of everything needing to go through the CPU, so let's say you want to load disk memory into main memory, it doesn't have to go first through the CPU, then to the main memory. It can go just from disk memory to the main memory. So in other words, it's a direct memory access. And So disk is an I/O device, and a few I/O devices have DMA, not just disk. And then finally, the Hello World program. So like, how would this run in a computer? Uh, it runs by, first you open your shell, your terminal, you compile it, and while you're typing in the characters in the shell, the keyboard, the input device will read each key, convert it to whatever the CPU recognizes the key or the command as, sends it to the CPU. The CPU registers what you're saying and displays it to the screen, right? And then when you hit enter, that enter gets processed and it says, oh, he wants to run this. And then the shell stops executing because the shell was sort of controlling the computer, right? The terminal reading your characters. Now the operating system is mainly working, and it's saying, oh, well, the shell first says, hey, operating system, like, I need you to go get this file and run it for me, because that's permission the shell doesn't have. And then the operating system will be like, okay, and it'll go to the main memory, to the disk, load in the hello executable to the main memory using DMA, and then it'll run it. And even the way I described it, it's much more complex. That's the simplest version. Section 1.5, caches matter. So the processor memory gap means data, the further away data is from the CPU, the cheaper it is in terms of money to build it, but also the slower it is. In other words, it can't get sent to the CPU as quickly. So, and it's an insane difference. Like getting data from a register, right? The way the CPU stores data instead of the disk is almost like probably a million times faster. Like it's that much of a difference. And or even main memory. So accessing register, fastest thing. Accessing main memory, second fastest. Much slower though. And accessing disk memory is insanely slow compared to the other ones. But of course, you can store way more data on a disk than you can on main memory. And then, of course, in register, you can access it almost instantaneously, but you can only store 32 bits in a register, or 64. Most computers now, 64. So the way to sort of make this more efficient is to implement static random access memory. And that's basically main memory on the CPU itself. And this is often represented as a L1, L2, L3, or even sometimes L4 cache. Of course, as you go down, the caches, or I'll explain that in a sec. So you have these caches, and basically, if you're working with a lot of data, in the main memory, you can just store it in the cache, or in an L1 cache for faster access, because now you don't have to go outside the CPU. It's just right on there. It's still slower than a register, though. And so you have like the L1 cache, the L2 cache, and then maybe an L3 cache. You could have as many as you want, really. But there's usually, I think, 3 or 4. And then maybe an L3 cache that is a cache for the L1 and the L2. So you can imagine going up this memory hierarchy. Let's just get into the next session. As one thing, one memory storing device being a cache for the next one. So registers, and then if you're using some data a lot, you put it in the caches or the SRAM. If you're using that a lot, you put it and the stuff you use less frequently, you put in the DRAM, less frequently disk, less frequently remote. What does remote mean? You're storing it on a server across a network, like 4 states away maybe, or just on a computer within your house, just over the network, remote. Okay, 3 more sections. 1.7, the operating system manages the hardware. Sorry to throw you off track here, but let me go back. I said I was going to explain buses better. I just remembered. I also forgot to explain what a word is. So computers don't exactly work with just bits, ones and zeros. They more read bytes, and byte is 8 bits. So a computer usually will read like a 3 byte or a 4 byte, right? So 2 being 16, 3 being 32, 4 being 64. And a computer will usually work either with 64-bit data or 32-bit data, 16-bit data, or 8-bit data. I mean, normally now it's 64. It hasn't been 8-bit for like 40 years, but and what it works with, we call a word. So of course there's 64 bits that you can work with maybe by splitting up into 232 bits if a computer can't handle it. But whatever it can, like the norm is, we say that's a word. And then buses, a possible implementation of a bus is you have a series of lines, electrical wires that carry a electrical current, and you can send 1 bit on these wires. So if you're sending 1 byte across to a different device on the motherboard being the board that contains all the devices of the hardware, it would split it up across 8 lines. But there's also another architecture for buses where you have what's called forget the name. I think it's parallel bus lines, or it basically is parallelism for bus architecture. And what it does is, instead of splitting 1 byte across 8 lines, it will just send the whole byte on 1 line in sequence. So like like 1 0 1 0 1 0 1 0, right? Instead of like splitting up all those ones and zeros across 8 different lines. Or it could do both, right? Okay, just wanted to touch on that. Okay, 1.7, the operating system manages the hardware. Operating system, not going to go over this because I already covered it. It's just the software that controls the hardware. Processes. Processes are the fundamental abstraction of an operating system. What does that mean? It means a process is basically what is controlling the hardware. What code is running is a process. Now, on some computers, you can only run 1 process. On some, you can run multiple processes. And of course, there's different ways of doing this. So for example, let's take a uniprocessor system. What does that mean? It means there's only 1 CPU with 1 core. Now, this means it can only run 1 process at a time. However, it can get away with running multiple processes at a time, actually. So a uniprocessor system can run your YouTube video as well as run music in the background. How does it run? So those would be, 2 processes right there. One for one application, one for another. How does it do this? It uses context switching. The human eye works slower than a computer can display things to the screen, right? So you could have 2 or use its execute instructions, let's say. So a computer can just rapidly switch between 2 processes and execute one instruction for one thing and then another for a different thing, and then just keep switching back. So that's called context switching. And it's a way to run multiple processes on a uniprocessor system. Then you have multiprocessor systems, with multiple processes, or multi-core systems, where in a CPU there's multiple cores, which means multiple ALUs, things of handling different instructions. And this is much easier to run multiple processes on this. You could even have on a multiprocessor system context switching. So you could have tons of processes running on one system simultaneously, or seemingly simultaneously. Simultaneously for sure because of the multiprocessors, but seemingly in another way because it can run even more than that if it uses context switching. Now, then we have threads. What are threads? Thread is basically a process, meaning like a control flow, like something that could execute, but within a process. So you have processes that can, that are basically synonymous with the programs that run on a computer. And then within each of those, you have threads, which are different control flows within a process. Control flow being this thing can do one thing while the other thread does another thing. Then you have virtual memory. Virtual memory is just how the programmer or everyone sees the memory as opposed to the operating system, right? Because the memory, the operating system could do a bunch of stuff wacky with the memory to make it more efficient, right? It could only store parts of files that are necessary in the main memory or the cache or however it wants to split it up, whereas you, the user, will just see it as one contiguous block of memory, right? And so this is called the virtual address space. And for a process, the virtual address space will have a few different things. One, it'll have the program, code, and data, so whatever data it works with, and the code of the instructions that you want the computer to execute. It'll have a heap and a stack, and those are dynamic areas of memory because they can grow or shrink, and different programming languages can access the heap and stack differently. I won't go over what they are, but just know that in most programming languages, when you're executing function calls and have data that's local just to one function, it uses the stack, and only sometimes does a programming language use the heap, mostly the stack. So it also has shared libraries, that you want to use, and also the kernel. And what is the kernel? The kernel is the fundamental part of the operating system itself. So it's almost synonymous with the operating system. And of course, the computer needs to store that data as well, so that gets put there. Also, files. Files are an abstraction for input-output devices. So a keyboard can be seen as a file. I know that sounds confusing. A disk can be seen as a file. That makes a little more sense. Or multiple files, right? So basically, input-output devices or file is an abstraction for input-output devices. Okay, super short section here, systems communicating with other systems using networks as section 1.8. All this says is, look, networks are common today. You can connect a computer to the network, and you can treat a network as an input-output device, just like a keyboard or a display or a disk storage. Okay, section 1.9, important themes. So this mainly discusses concurrency and parallelism. So this book defines concurrency and parallelism a little different than I've seen in the past. It says that concurrency is sort of the general concept that things can execute at the same time, whereas parallelism is it actually doing that. However, most of the time I see these defined as concurrency being things are executing at the same time and working with one another, whereas parallelism is things executing at the same time but not working with one another. I think those are better definitions for those terms because they actually mean two different things. Multi-core, I already discussed. It's a single processor with multiple ALUs and stuff a CPU would need. Take what a CPU needs, times it by 4, and boom, you have a multi-core processor. Hyperthreading. Hyperthreading is the idea that one core can actually execute two things simultaneously. And how it does this is whenever you're using a core, there are some parts of the core that tend to not be used because they just don't need to be. And what hyperthreading is, it basically more efficiently uses a core so that one thread can use one part of the core while another thread uses the other part of the core. So that's hyperthreading. Instruction level parallelism is where instructions are being executed in parallel. So what does this mean? Well, first, when we go through an instruction, what usually happens is you fetch the instruction, you decode the instruction, and then you execute the instruction and output it or display it or whatever, right? It follows this pattern. And if you just send one instruction into the core, right? It does the first thing, waits, does the second thing, and then does the third thing. Why everything else is waiting for it to go through this process. So core can utilize pipelining, which means as soon as the first instruction is done with one thing, send the other instruction in there to do that first thing, right? So for all example, 5 stages of a core that an instruction will go through, you have 5 different instructions at each stage working. Now you also have SIMD parallelism. This stands for single instruction, multiple data parallelism. Now, what does this mean? Oh, sorry. Superscalar processors are basically processors that have instruction level parallelism on, and it's to a high degree. Okay. SIMD parallelism. So that's let's say you want to add these two numbers and add these two numbers and then add all four of those numbers together. So that's one instruction, single instruction, right? SI, and then MD, multiple data. You have four different numbers. This means you can add all four of them at the same time. So that's SIMD parallelism. Last concept, virtual machine, is basically, what is a machine? You can think of a machine as a computer system, right? So hardware and software that can run an application program. A virtual machine is this, except it's entirely software, but it simulates both a hardware, it simulates its own computer. So you could, have a virtual machine on a computer, which is basically like its own computer, even though it's still using the hardware. It's just an abstraction to say like, hey, this is its own sort of operating system hardware set, even though it's just software, still running on the same operating system. All right, that's the end of this chapter. Sorry it was so long. Make sure to give a like if you like this video. Make sure to subscribe to see the rest of this textbook review, as well as my other textbook reviews. And make sure to leave a comment if I missed anything, if anyone wants to add anything, or if you have any suggestions for further textbook reviews. Thank you and have a nice day.